Hey everyone, I'm Sophia, and today I'll be walking through a demo of SmartCookie, which is a split proxy approach to in-network SYN flooding defenses against large-scale DDoS attacks. For the full details of our system and our work, please refer to our paper. So today I'll be showing the performance of our system in terms of latency and CPU, and what I'll do is I'll first walk through kind of the setup that I have here, and then I will show the baseline performance without any defense and without any attack. And then I will set up the defense, show how to set it up, show the parts that are necessary, launch an attack, and then show the performance in terms of latency and CPU usage while our system is under attack. And you're going to see that the performance remains really close to the performance of the system while it's not under attack once our defense is turned on. So first, to orient ourselves a little bit, on the right side of the screen here, I have 5 terminals which are dedicated to my server, which will be running my SmartCookie server agent portion of the defense, and it'll also be running a simple HTTP server script that will serve out HTTP responses to requests made by clients. And then on the bottom middle terminal here, what I'm calling my JC5 server, this is going to act as my client, and this will be generating HTTP requests to my server, then measuring the latency, the end-to-end latency that includes the connection setup and the handshake portion, the downloading of data, and then connection close. Then finally, my JC4 server over here is acting as my attacker, and it's going to be using package-gen DPDK to generate SYN flooding attacks and also ACK flooding attacks. This final terminal on the left here is for my Tofino switch, and this will be running Tofino programs, and it'll also be running my SmartCookie switch agent portion of the defense. So first, I'll show the baseline performance of the system, and the first thing I'll do is I'm going to load a simple wire program. This is called my basic subnet wire, and essentially all this does is it takes packets in from one port on the switch and forwards it out to the proper destination. So it's really just acting as a forwarding switch here. And I'm going to load this onto my Tofino switch, and then I'm going to start up my HTTP server over here. So that's started up. There's no output, but this is running now. And then over here, I'm going to run some commands that basically just allow me to add and bring up the desired ports on the switch. So it's just adding a port with a specified capacity, etc. So I'll paste in a few commands to do that. And then we can see that the ports that I currently need, these two, we can see that they're up and running. Okay, so now, once I have my switch with basic forwarding running and I have my HTTP server running, I'm going to show my baseline latency for a client, a legitimate client with no attack ongoing. And I'll do that by running this command. That's basically taking as input some source port that I want and some other kind of log keeping information. And we're going to see that the baseline is about 1.1, 1.2, 1.3 milliseconds. This is end-to-end latency again with connection setup, download, and the connection teardown. And we're also going to see that on the server side, the CPU usage is really quite low. There's nothing much happening on the server. So this is the baseline latency and CPU performance. Okay, so now what I'll do is, again, bringing up the basic forwarding program on my P4 switch. Oops, I'm missing a command input. I want to demonstrate what the baseline latency and CPU performance look like under attack without any defense. So first we'll bring up everything on the switch again. Let that come up. We'll bring up my attacker. And for the attacker, I'm going to copy and paste in a bunch of commands that will basically launch the attack. And I'll explain a bit more about these commands later on in the video. Basically, these commands will set a bunch of SYN packets to flood towards the server. And on the server side, I don't have any defense running. I will run my HTTP server again. And also what I'll do is I'll turn on a packet counter, just counts the number of packets I have. Then I'll also show what my CPU usage on the server looks like. And so here basically on the server, I have no defense, just a regular HTTP application running. I have not started the attack yet. You can see that no packets are being generated. And then over here on the switch, I have a basic forwarding program. Nothing's happening there yet. And so what I'll do now is I will start up the attack. And so you'll start to see some activity. Basically, the packets are being generated over here. It's a little hard to see over here. These are being sent. This is what's received back. And on the switch, we can see what that looks like is the packets are being sent by the attacker machine, received on this port, forwarded to the server machine. And the server machine is responding at this rate. But we'll see that now we'll see what the latency looks like. So let me choose a random number. I need to specify a demo. Okay, right. So a few things to note here. First, I did not update my script, so actually these are writing some values to this file, this folder that you can just ignore the name. This isn't a relevant name for us at all. This isn't necessary for what we're doing here. All that we care about are these numbers here that are being printed out to the terminal. And so essentially you can see values much greater than 1 millisecond, particularly this one here. And what we are experiencing as a legitimate client is, as our server is having to handle the SYN flooding attack traffic and having to respond, do cookie checks, etc., it's starting to become overloaded. And you'll see that the CPU is, one of them is just really maxing out here. But what ends up happening is some packets start to get dropped, and then legitimate client requests get dropped as well. And so let's see what happens if we raise the rate of attack. So now what we have is we're sending at a rate of about 30 million packets per second. Let's again see, let's randomize this here. Let's see what our system kind of looks like. So you'll see the program is indeed running, but we're just running into a lot of packet drops and a lot of performance issues. So it's possible that a request might not even complete. We'll have to see. Okay, what I'll do is I'm going to lower the rate slightly, try running the command again and see if that helps. Okay, all right, so one request completed, and that took 8 seconds, which is quite a lot of time, much greater than the 1 millisecond baseline that should be the performance for a legitimate client if the server weren't under such an attack. And so let's see, this was at an attack rate of barely 18 million packets per second, not even 18 million packets per second, and this is the huge drop in performance that we're seeing. And so this the script that I have here, this should run the latency request 2 more times, but it looks like we're kind of hitting a timeout here and probably should go and try to reload our application at this point. So I'll let this run for a few more seconds, but it's quite likely that won't run. Can try lowering the attack rate, see if that helps. So now this is at an attack rate. Oops, I need to change. So the reason why this was 10 milliseconds was that without the source port changed, this triggered an existing connection, and so that changed the latency. But let's choose another random source port and see how long this takes. This is at an attack rate of almost 12 million packets per second. Let's see if this request is able to complete in some reasonable time. Okay, so that one took 12 seconds. And so the packet dropping is also rather random. Okay, this next one took 3 seconds. And so not all clients will even experience the same breakdown in performance. But it's clear to see that without any defense, the SYN flooding attack can really get out of hand in terms of performance. So I'll stop the attack now and move on to the next part of the video. Now what I'm going to do is I'm going to stop my simple forwarding program, and now I'm going to run my SmartCookie switch agent defense. So I previously already built the program, so I won't build it again because it can take a little time, but I want to show the command. The command to actually build the program is just this p4 build command, and then you'll pass in the program name. This happens to be my program name. And so you would run this and it would build. But since I've already built that, what I'll do is I'll just load the program onto the switch, and the command to do that is this, and then that'll run, and that'll load, and that'll take a few seconds. And once that's done, I again copy and paste in the commands that I need to bring everything up. And if I look, again, the 2 ports that I'm interested in currently are up and running, so that's good. In the meantime, on the server side, what I'm going to do, I'm going to bring up the SmartCookie server agent. And that's basically, I have a Python program that's loading some eBPF code. And once it does that, you can see that I have my XTP ingress program loaded and I have my TC egress program loaded. So the SmartCookie server agent is up and running and ready to go. I'm also going to run my HTTP server once again. And you might have noticed that there's a slight activity on my server-side CPU now, but it's really quite minimal. Nothing much is happening still. Alrighty, so as you can see, we have our SmartCookie switch agent up and running on the left. The server agent is running on the right, as is our HTTP server. Now we can just go ahead and collect some measurements on our client, some latency measurements. And we'll choose a random source port for this. So as you can see, our latency is quite similar to the baseline latency without the defense running. So one more thing I'll show is just a counter of the number of received packets on the server that we're running. And currently we're not receiving any packets. There's nothing really happening. And so this counter we can use to keep track of once we start up the attack, excuse me. So to start up the attack, now on my attack machine over here, I'll run a few commands that will basically start up my packet gen DPDK program with the necessary configurations. So now that's starting up, and then what I'll do is I'll run a bunch of commands that will start up the actual attack. So I'll type in a few and then I'll copy paste them over, but basically this is setting the packet type to be IPv4, setting the count to 0 for the specific port is going to say send unendingly, just send infinitely. We set the burst amount, so the number of packets sent at one time, to a high amount. We'll start the rate out fairly low. And then here now what we're doing is we're actually crafting the packet. So this is where I'll copy paste in a command. But this command basically sets a random mask at a specific offset and sets specific flags, specific bits in the packet to signify a SYN packet. So that's a SYN packet. We need the TCP protocol. We want the packet size to be 40. And then we set source MAC and destination MAC. And then copy paste in some more commands, put source and destination IP addresses. And so these can also be randomized. You can also read out packets from a PCAP, and so make them as randomized as you want. For the demo simplicity's sake, I'm actually just generating packets in this manner, but for our actual experiments, we also used PCAPs with real traffic traces. All right, and so now we can actually start up. Okay, cool. So I started the packet generator, and what you'll notice is the rate. So this is the rate of packets that are sent and the rates that's received back. And so these are all SYN packets, and what we can do is we can look over here. I'll clear the screen a little bit, but we can look over here and we can see that on our JC4 machine, which is this one, we're getting a certain number of packets received at the switch by this machine and then sent by the switch back to this machine. And so really what the switch agent is doing is it's receiving all of these SYN packets, generating SYNACK packets, and sending them back. But you'll notice that no other packets are sent to any other servers, and in particular they're not sent to the actual destination server, which is this over here. So no matter how many SYN flooding packets are sent, everything is completely stopped at the switch. All the SYN packets are properly processed. A secure cookie is generated. The cookie is returned to the either attacker or to the client, and then the number of SYN flooding attack packets that are received by the server is actually 0. So SYN flooding attack packets are never received by the server. And so you can see that we can run our latency measurement script again. We'll come up with some randomized source port to start at. We'll check out what the latencies are. And as we can see, the latencies still remain quite low in the 1 millisecond range, and of course that makes sense because none of the SYN flooding attack packets are actually being reached at the server. And so that's the end of the demo for the SYN flooding attack, for how our SmartCookie system operates under SYN flooding attacks. What's really cool is that our SmartCookie switch agent completely handles 100% of the SYN floods, and so that means that the server isn't affected. Those packets aren't actually reaching the server, and so the client latency and then the server CPU usage, the performance remains quite excellent and very close to the actual performance of the baseline without any attack going on. While I have everything running here, I can actually show if we set the rate to be higher. So I'll just start pushing the numbers up a little bit. I'm not actually sure. You see the number jump up. Now we're sending almost 18 million packets per second. I can push this up to around 35 million packets per second. And we can see SYN flooding packets are still being all stopped at the server, at the switch agent. Nothing's getting to the server, and so the latency and the CPU usage remain low. For completeness sake, I can actually go ahead and show what a latency measurement looks like under this setting as well. Again, I'm going to choose a random source port. And we're going to see that the latency remains low near the baseline. So that's the end of the SmartCookie demo against SYN flooding attacks.